Hey everybody, we are ready to talk about chemical equilibrium. Equilibrium, equilibrium, equilibrium. So we have to define what equilibrium is because there are lots of misconceptions as to what it means to be equal. Okay? Equal doesn't necessarily mean the same amount. What it means is that the rate of the forward reaction and the rate of the reverse reaction are the same. So it's all about the rates, which is why we studied kinetics before we studied anything about our equilibrium. Okay, so this right here can technically be at equilibrium. It doesn't mean that both sides of our seesaw are equal. It just means that they are happening at the same rate, which means they are both very, very still, so nothing is happening. All right, so chemical equilibrium is going to be when you have no change in the concentrations of the reactants or the products. Okay? Remember, everything is in constant motion. Okay? So what that means is that even though there is the outside opinion or it looks like something is still, it's not still. It just means that the forward and the reverse are happening at the same rate. And if they happen at the same rate, it looks like it's still, but it's really not. So your reactants are going to turn back into products, and the products are going to turn back into reactants in a reverse process. It still means it is moving. Okay, the only time that is moving or it is not moving, what's that only criteria? At absolute zero. Okay, so we're not talking about anything at absolute zero. That means that these substances are going to be moving in the same amount. All right, so this was one of my favorite little slides here. All right, so like if you see a whole bunch of people in Narnia and only a couple people in Middle Earth, they are going to move across and trek across the river into the other side. And then all these Middle Earth people are like, ugh, I don't want all these Narnians here, so they move back. So then they end up seeing that they're basically constantly shifting back and forth in this equilibrium because they may or may not like their neighbors. It doesn't necessarily mean that we end up having the same amount of neighbors on both sides of the river. Okay, so what we're going to do is we're going to take a look at our smog in the atmosphere. Okay, so we end up having NO2 gas that is emitted from cars, and the N2O4, which is the colorless gas in our atmosphere. And the N2O4 is going to make 2NO2, and the 2NO2 is going to make the N2O4. So basically, those are the two types of reactions that we have. Right? So what happens in a chemical equilibrium? The forward reaction still occurs, but the reverse reaction occurs at the same rate. So if this is the forward, N2O4 making the 2NO2s, the reverse reaction starts happening also. So we see these double-headed arrows. So you can see them written like this. That's usually the best one that I can get for our PowerPoints and our Google Slides. In real life, I usually write them this way with a half forward and a half reverse reaction. You might see them written this way, or you might see a double-headed arrow that looks like this. All three of those things mean exactly the same thing, which means that your forward rate and your reverse rate are going to be happening at the same speed. Okay, so this is what it would look like, and it's really this simple for this reaction here. We have our N2O4, and here we have our 2NO2, and you'll notice that the bond here is broken. So sometimes they collide with the proper orientation and sufficient amount of energy and make it, and sometimes they collide and break it. But we end up seeing that we have this amount of equilibrium. All right, this is what it would look like. You have some of your clear gas and you have some of your brown gas up here, but it's going to occur constantly, and eventually it looks like it is still, and it looks like it is not moving. So if it looks still, and I don't know why I did and not moving, okay, that means it's at equilibrium. But is it still moving? Yes. Okay, it is just moving at the same rate, so it looks still. All right, these graphs right here show what happened when we start with different amounts of our reactants and different amounts of our products. Okay, so here we're going to start with no NO2, so this is start, and this is end. Here we're going to have a 0.4 molar concentration of N2O4. Okay, so what happens to the N2O4? The N2O4 is going to decrease. This is our reactant. The reactant is going to decrease until it gets to this point. And what's going to happen to our product? Our product is going to increase as the reaction occurs until it gets to this point. And then this point right here is where they establish chemical equilibrium. And then you see they both flatten out. So we have the same concentration of both. It doesn't matter what you start with and what you end with. So here we have no product, we have no reactant. And here we have lots of product. Okay, so you see the product is going to decrease until this point, and you're going to see our reactant is going to increase until this point. And guess what? It will all even out so that we have the same concentration of each. And this is obviously going to be dependent on temperature. We're not going to really get into that in our chapter, but we're going to make sure that we have the same amount that is going to be produced and broken apart and at a constant equilibrium. Okay, so as equilibrium approaches, the concentration of the reactants will decrease and the concentration of the products will increase, no matter what you start with. And then you get to this constant amount where you have your reactants being formed and your products being formed in the same amount. Okay, so these reactions are called reversible reactions. So the rate of this reverse reaction is going to speed up, the rate of the forward reaction is going to slow down, and then you get to this magical sweet spot where you are at chemical equilibrium. The forward and the reverse rates, not amounts, the rates are equal. And that's what's really important to remember with these types of problems. Okay, so at equilibrium, the forward reaction decreases, the reverse reaction increases until the most important part, the rate of the forward reaction and the rate at which the reverse reaction are produced are exactly the same. That's when we have reached a nice reversible reaction and you are at equilibrium. Okay? So that is the biggest thing to remember about it.